Hi, Dr. Smallwood. So this is the final project for Physics 130. My name is Yik, and now I shall begin. So today I'll be talking about the convolution theorem and how this is actually applied to image processing. And I'm going to show a proof of it and also show an example using the Dirac delta function. And finally, I will show an example using the impulse response function. So let's begin. Okay, so now I'll be running some Python code to show what this does. So basically, one of the examples in image processing, one of the examples of convolution theorem is image processing. So you can see here on the left-hand side, we have our original image of myself. And on the right-hand side, you have a kind of black and white inverted image and also like a blurred out image. So for example, you can see my hair strand on the side. There, it's kind of blurred out. So what I did with this Python code here using the OpenCV library is that I kind of just basically pass it through some filters, and this is what we have in the end. So why is this really important is that it's because during optical character recognition or image processing, especially during machine learning, we want to kind of remove all these noise or kind of smooth out these very how do you say it, very noisy kind of stuff. So that's why we need to apply these image processing stuff before we can pass into the machine learning algorithms. So convolution theorem is actually really important because it helps us to do stuff like image blurring or like Gaussian blur or medium blur. So yeah, so right now I will be showing how we prove the convolution theorem. Okay, so first of all, the function, let's say that we have a function of h of x is equal to negative infinity to infinity, and we have one function and then another function that we pass through with some delay. If we want to prove that the Fourier transform of this function is equal to h of k is equal to 2 pi times f of k times g of k. Okay, so what are we going to do? So the first thing we do is just we do our normal Fourier transform stuff. 1 over 2 pi is equal to negative infinity to infinity, and we copy down hx. We get negative infinity to infinity, f of t, gx minus tau, d tau, e to the negative ikx, and dx. And the next thing we're going to do is we're going to let w is equal to x minus t. And then, therefore, this means that x is equal to w plus t, plus tau, sorry. This will be 1 over 2 pi, negative infinity to infinity. And we're going to substitute it in f of tau, g of w, d tau, e of negative I, k, and then w plus tau dx. The next thing we're going to do is we're going to split this exponential term here and kind of group them together. So we get 1 over 2 pi, integrate negative infinity to infinity, f of tau, e to the negative ik tau d tau, integrate negative infinity to infinity, g of w, e of negative ik w, dw. Sorry, this one should have been dw because we have a change of variables. And then we observe that there is this function here. And there is also this function here. Do they look familiar? Yes, they do. They're just the Fourier transforms of f of k and g of k. And then we have to just multiply another like 1 over 2 pi here and then multiply 2 pi by the side to get the form that we want for Fourier transforms. So the answer will be 2 pi of f of k and g of k. And voila, that is how we got that is how we prove the convolution theorem of the Fourier transforms. And then one example here that we have here is that let's say that we want to do the Dirac delta function, which would be h of x is equal to f of r null times Dirac delta function of delta r minus r null dr. And then we just apply the convolution theorem here, 2 pi f k g k, and we get 2 pi f r null delta r null. And then because the delta of r null is equal to 1, it is just 1 at that point. So just multiplying by 1, the answer will be 2 pi f of r null. So if we just disregard 2 pi, this is actually a sifting theorem. So basically what this does is that if we look at the Dirac delta function, we take the convolution theorem of it, we do the convolution of it, what it does, the Dirac delta function actually sifts out this specific point in this function. So this is one of the most powerful properties of the Dirac delta function, because it can just single out one single point that we need from the input function. And yeah, so right now I'll be showing a real example and showing how this would relate to image blurring. And I will be doing this using the impulse feedback function. Okay, so right now we see that we have a very spiky function, and then we're passing in an impulse function of h of t, which is a rectangular function, and see how this convolution theorem, after it can be expressed as a multiplication of two functions, we see that it kind of smooths out the entire curve of this very, very spiky function, and then it becomes very, very curvy in a sense. So this is actually really important. This is actually how the image processing is done, because we take an image and then we apply some kind of impulse function to it, and it will kind of blur and smooth out the entire image and reduce like the resolution a little bit. So yeah, this is kind of like the background that's happening in the application for image processing. And that concludes my video, and I hope that you've understood and learned something. Thank you for listening.